For 1.1, the consideration that we have to make is what would happen in reality if I added water to magnesium chloride. And absolutely, some water would be taken in as water of crystallization. But I can't guarantee that this is the only reaction that would happen. In fact, there's another reaction far more likely to happen, which is that the MgCl2 breaks down into Mg plus 2 aqueous and 2Cl minus aqueous. And what that means is, because the MgCl2 is soluble, I cannot determine what the enthalpy change would be purely for the reaction that we can see here. Now we can use alternative methods, and we're going to build a cycle here. We're going to start by showing the equation for what we want to know the enthalpy change for, and I've got my little X above the arrow. And I need to know what enthalpy of solution means. So using that, I can then complete my cycle, and this is precisely what I was talking about in 1.1, the potential error, that if I do put MgCl2 in water, my enthalpy of solution will be the enthalpy change to get to Mg plus 2 aqueous and 2Cl minus aqueous. Now you'll notice this isn't balanced for water, but that doesn't matter for what we're going to do for the calculation. What does matter is that I've got the values minus 155 and minus 39, and I can also identify my two routes within the cycle. They both start at MgCl2 solid, and they both end at Mg plus 2 and 2Cl minus, both aqueous. With that in mind, I can now make X the subject. I can find my two routes, I can rearrange to make X the subject, and I get my enthalpy change of minus 116 kilojoules per mole. So a 6 marker, and a 6 marker based on a required practical. So you need to be on top of your understanding of process and procedure for how we actually carry these things out. So you have got to describe how you would carry out an experiment to determine the enthalpy of solution of anhydrous magnesium chloride. And it's telling you to use around 0.8 grams. How are you going to use your results to calculate the enthalpy of solution? Well, there's three components to this. There's the method, there's the measurements you'd take, and there's how you would use the results. And we're going to go through each of these in turn. The method, we're going to measure the water with named appropriate apparatus. You can't just say you're going to measure the volume. You would need to say you're going to use a measuring cylinder or something suitable. You're going to get a suitable volume or mass. Now, you need, as a volume, it's actually a very wide range, anywhere from 10 to 200 cm cubed per gram of anhydrous magnesium chloride. So if you went for 100 cm cubed, you would not go far wrong. That puts you well within the range. You're going to put it into an insulated container, a polystyrene cup. You can't just say you're going to insulate by putting a lid on. You do need the idea that it's an insulated polystyrene cup calorimeter. You're going to add a known mass of MgCl2. This said to use about 0.8 grams. You can't just say add the MgCl2. It has to be a specific mass. You might have said 0.8, you might have said close to 0.8, but you need to specify a mass. And you're going to use before and after weighings. Not with washings, because that's actually going to start dissolving any of the excess if it's still in there. So you would need to do this by the mass of the weighing boat plus solid and the mass of the weighing boat after you've added it. So you've got to have that level of specificity within your answer. In terms of the measurements, you're going to record the initial temperature, and you're going to do that for 3 minutes. That's your measurement of the volume temperature, the liquid temperature, for 3 minutes. And then, if you remember these with the cooling curve graphs, at the 4th minute you would add your sample, and then at the 5th minute and at regular intervals you're going to measure the temperature to get the cooling trend. And it's a graph that you've got to be really familiar with, that you need to be ready to draw and use to calculate the delta T for a Q is MC delta T calculation. You're going to plot that graph of T versus time. So we've got the method, we've got the measurements, we can now consider the use of results. So because you've taken the temperature for the first 3 minutes, and that's probably going to be quite flat, you can extrapolate that line forward until it reaches the 4-minute point. You're also going to extrapolate the cooling curve back to 4 minutes. Now you're going to be very careful here that you don't include any where the temperature is still rising. It's only the cooling component that you will extrapolate back. And then you're going to calculate delta T. You're going to look at what the temperature would have been had we not added the solid at 4 minutes, and you're going to calculate what the temperature would have been at 4 minutes had the reaction taken place instantaneously. And that's what the purpose of the extrapolation is. We're assuming what the temperature would have gone up to had the reaction taken place immediately and there had been absolutely no heat loss to the surroundings. We're then going to use Q equals mc delta T. We're going to substitute in the mass of the surroundings. That's going to take into account whatever volume of liquid you used, assuming a density of 1 gram per centimetre cubed. We're going to use the delta T from the graph. We're going to use C, which would always be provided. It's 4.18, and we find Q. Once we've found Q, we're going to find the number of moles by looking at the mass of MgCl2 and its MR to find how many moles were added, so that we can convert our joules that we got in the Q is MC delta T calculation into kilojoules per mole. Now that's a very convoluted way of doing it, and you might want to show the calculation using sample figures, and that would be absolutely fine. To get level 3, to get 5 marks or 6 marks, you need to get all 3 of the stages, method, measurements and use of results, virtually correct. To get a level 2, 3 or 4 marks, 2 of them have to be perfect, or you have to have had a good stab at all 3 of them. And to get a level 1, 1 of those stages has to be virtually correct, or 2 of the stages have to be partially correct. We then have a graph drawing task and some calculations based on what you've drawn. So you have got to be very, very careful when you're plotting. It can be one of those things that people can rush through because it seems easier and simpler. Take your time, because it is easy marks, but it's easy to make a careless error and lose those marks. You put those in, and as you plot the ones that we have here, you can see actually that it's pretty much a straight line, but you're going to use a ruler to confirm that, and you put the line of best fit in. Now, you will get a mark for the 5 correct plots, you will get a mark for the straight line of best fit. You'll also notice here that I've added in a horizontal and a vertical line, and that's because we are going to need to calculate the gradient. Now, we are interested in delta G, and delta G is delta H take T delta S. Now, a really common comparison that is made within exam questions is how delta G equals delta H take T delta S is linked to Y is mx plus c, the equation for a straight line. I've rearranged here the delta G equation so that we can see what each component is. Delta G is negative T delta S plus delta H, which means that the X is negative delta S. And that's really quite useful, because I can calculate the gradient. I've got the figures here, 7.2 and 43. And from there, I can work out the gradient, and I can see that the gradient X is negative 0.167 kilojoules per Kelvin per mole. That's changing Y over changing X, 7.2 divided by 43. From there, I get that delta S is 167 joules per Kelvin per mole. So I've converted back to joules per Kelvin per mole by multiplying by 1,000.